Welcome back to part 6 on inverse functions. We just have a few examples left. In example 6, we have f of x equals 3 minus x all over 4, and the inverse is claimed to be g of x equals 3 minus 4x. We can check or prove whether these two are inverses of each other by composing them. Let's compose f with g of x. That will give me 3 minus the quantity, 3 minus 4x, all over 4. If I simplify that, I will get 3 minus 3, distributing the negative to both, plus 4x, all over 4. And then subtracting 3 minus 3 adds to 0. That gives me 4x over 4, and then reducing my fraction gives me x. So we've proven that one direction of the composition works. Now let's try the other direction. We need g composed with f of x. So now f of x is the inside function. So I have 3 minus 4 times the quantity, 3 minus x over 4. Simplifying, I get 3 minus the quantity, 3 minus x. Notice that I can reduce the 4 in the numerator and denominator of that substitution. Now distributing the negative, I get 3 minus 3 plus x. And clearly that will give me just an x. So since the compositions, regardless of order, both give me x as the final composition simplified, I know that these two functions, f and g, are inverses. All right, now let's move on to example 7. In example 7, we need to use the graph of f to sketch the graph of f inverse. The graph of f inverse is obtained by reflecting the graph of f over the line y equals x. And just for a reminder, the line y equals x is a line with rise of 1 and run of 1, centered or intersecting the origin. So it's this diagonal line through your Cartesian plane. And if I were to assign coordinate points for each one of the obvious points on this function f, we can then identify what we need to reflect. The first coordinate point is -7, -2. That is the far left coordinate point of this function f. The next coordinate point is at -4, 0. The next coordinate point is at -2, 6. And the last coordinate point that's obvious is at 2, 8. What I need to do is I need to reflect these points about the line y equals x. And I'm just kind of drawing these arrows so you see the general trend in what this should look like when I reflect it. And I just want to provide some information about how you can think about this. If this is really hard for your brain to figure out, one of the ways you can think about this is if you were to set a mirror along this diagonal line, what would the mirror be reflecting? In reality, it would show the exact same image on the left side as it would in the actual mirror itself. So you are mirror imaging it about the line y equals x. This gives me switched coordinate points. So now if I start at -7, -2, I will reflect it by changing the order of the coordinate points. My -2 is now my x, and the -7 is going to be my y. So now I will have -2 -7 as my coordinate point. The next coordinate point I'm reflecting is -4, 0, which means I will be at 0, -4. The next coordinate point I'm reflecting is -2, 6, so that will be 6, -2 in my new reflected point. And the last one I had was 2, 8, so I'm now going to reflect that to 8, 2. Now I will connect the dots. And you can see how the original function has been flipped about the line y equals x. Another cool thing you can do with this is take a piece of paper, fold it into 4 equal pieces, and then fold it about this line y equals x. And then any function that you originally drew, you can then translate or flip about that line.